VLSos here. This is a video lesson on behavior from derivatives. In a recent previous lesson, we talked about the various types of behavior or features that a function can have, what their names are, and a little bit about how you discover them and justify them. What we're going to focus on now is some behavior that's justified by calculus and how precisely to do that. What we're going to do is we're going to analyze a very familiar simple function, parent quadratic, whose graph is this familiar parabola. And the first thing that we're going to do is we're going to informally list or analyze this and list the behavior or the things that we could say are features of this function. This is done by just looking at the graph, so it's informal, but it'll give us an idea of what to expect. We should be able to justify that this function has a minimum at x equals 0. This point here is the lowest point amongst those around it. And being the only minimum, it will also be the absolute minimum for the entire function. We want to say that this parabola is decreasing on an interval from negative infinity all the way up to 0. Decreasing from negative infinity to 0 and increasing starting at 0 forever after. Increasing on the interval from 0 to infinity. Start here, it keeps going up. And this parabola is concave up everywhere, or concave up on the interval from negative infinity to infinity. These features ought to be easy to see from this familiar graph. But how do we justify them with calculus, formally? Well, we know that the function is parent quadratic x squared. And we can use the power rule to find the derivative quite easily. Bring the exponent out in front, multiply, reduce the exponent by 1. Here's how to justify that we have a minimum. Remember that we can visualize tangent lines, and when we have a tangent line at an extrema, in this case a minimum, the tangent line is going to be horizontal. It's going to have a 0 slope. Well, where a function's derivative is equal to 0 are places that we would look for minimums and maximums. So if I have the expression for the derivative, 2x, and I set the derivative equal to 0 and find all of those x values where the derivative is 0, in this case I get one value of x. And the value of x that makes the derivative 0 is 0. We call this, the location where the derivative is 0, a critical point. Critical point highlights the fact that I'm going to expect to be able to further justify that I have behavior there, interesting behavior, like extrema. So how do I do that? I'm going to make what we call a sign line of the derivative. This is a number line, and I've placed the critical point 0 on the number line. I'm doing this so that I can analyze the sign, that means positive or negative, the sign of the derivative before this critical point and the sign of the derivative after. I have the equation for the derivative. Let's imagine putting negative values into the derivative. Those are values before 0. If I put any negative value in for x, then the derivative is going to be negative. If I put in a negative value, the derivative is going to be negative. I can show that on a number line where this is the domain of the derivative, f prime. How about values after this critical point at 0? Imagine putting in a positive value like 1. If I put 1 into the derivative equation, then I'm going to get a derivative that is also positive. Put a positive number in, get a positive derivative out. So what I've shown here is I've shown that the derivative of this function is negative all the way up to 0 and then positive afterwards. tangent lines are sloping down, and then the tangent line becomes 0, and then afterwards tangent lines are sloping up. This will always be the case if this critical point is a minimum. And in fact, setting up this justification formally justifies that I have a minimum at 0. Negative derivative before, 0 derivative at the critical point, and positive derivative afterwards. I know that I have a minimum at x equals 0. How about decreasing? A function is always decreasing where its derivative is negative. This sign line that I set up also prepared me to show that the interval of where I get a negative derivative is also the interval where it is decreasing. Formally, to justify a function as decreasing, you show where its derivative is negative. And to show where a function is increasing, you show where the derivative is positive. This sign line is showing that I have a negative derivative, so it's decreasing from negative infinity to 0, which I've stated here, and the derivative is positive from 0 to infinity, which I stated here. How about concavity? Concavity is where the second derivative it's concave up, where the second derivative is positive. Negative second derivative means concave down. So if I have the derivative of the function and I take the derivative again, I will get the expression for the second derivative. The derivative of 2x is 2, which is a constant function, and it's constantly positive. So the second derivative is always positive, which means that it's always concave up, which is the last thing on the list of behaviors and features that I wish to justify. Let's do this again with another fairly simple function that we're familiar with. A cubic curve. First, informally, we're going to list the behaviors, and then we're going to formally justify them. This is not all the behaviors that can be listed for these functions. These are the ones that take some calculus to justify. I would expect that there would be no extrema. The cubic curve goes to infinity in both directions, but nowhere along the way does it have a high point or a low point like the parabola. The cubic curve is concave down from negative infinity up till 0. Concave down like an umbrella that sheds rain, and concave up like a bowl that will collect water from 0 to infinity. Or CCD on the interval from negative infinity to 0, and concave up from 0 to infinity. The cubic curve is also always increasing. It's always headed up as x increases. So we could say always increasing. And concavity changed, so we could highlight that we would have an inflection point at x equals 0. An inflection point here where the concavity changed. How would I justify these things? First, the function, x cubed. And I am immediately going to take the first and second derivative, knowing that I'm going to use calculus to justify these things. I'll prepare the first and second derivative right away. First derivative, bring down the 3, reduce the exponent to 2. Second derivative, bring down the 2 to multiply the 3 to get 6x, and the exponent went from 2 to 1. Now, I don't have any extrema, but I need to still attempt to find what we're going to call critical points, where the derivative is 0, and then justify why the derivative is not a local minimum or a maximum. So I take the derivative expression, 3x squared, and I set it equal to 0. I want to know what, if any, values of x make the derivative 0. And if I solve this for x by dividing by 3 and then square rooting, I can see that when x is 0, the derivative is 0. Just like the parabola, I do have a critical point at 0. So let me attempt to make a sine line. This is a number line for the sine of the derivative. And the critical point is a tick mark at 0. And I'm going to think of numbers before 0 and use them to determine what the sign, positive or negative, of the derivative is. So before 0, I have any negative number. Put in -1 to the equation, and it squares, becomes positive, multiplies by 3, and stays positive. So the sign of the derivative before 0 is positive. Put in any negative number, still get a positive derivative. Afterwards, after 0, I could test a number like +1. Put +1 in, square it, multiply by 3, I get a positive derivative. The sign of the derivative did not change. It's always positive. Except at 0, the derivative is 0. We have a horizontal tangent line there. But it's not a minimum or a maximum because the sign of the derivative didn't change sign. It was positive, then 0, and then kept being positive. So we're increasing before 0, 0 derivative at 0, but then also positive increasing again. No extrema. The sign of the derivative did not change. How about always increasing? A function is increasing where the derivative is positive. And I've shown in this sine line that it is increasing here because it has a positive derivative, and it's increasing after 0 also. So it's not always increasing, to be precise, because it's increasing everywhere except at 0, where there's a 0 derivative and 0 is not positive. So always increasing, but not at 0, to be precise. Stuff that in there. Okay? To talk about concavity, I need to consider the second derivative. The second derivative is 6x. So I can analyze with a sine line the sign of the second derivative. The second derivative is 0 where x equals 0. Again, if I set 6x, the expression for the second derivative, to be equal to 0, then the value 0 for x is where the second derivative is 0. I'm making a sine line to show the sign of the second derivative. It's going to be 0 here, but what about before? If I put a negative number into the second derivative equation, a negative number times the positive 6 will always result in a negative second derivative. After 0, if I put a positive number in, then a positive number times positive 6 will always result in a positive second derivative. The second derivative talks about, or is evidence of, concavity. Where the second derivative is negative, it's concave down. The sine line has shown, after consideration, that it's concave down from -infinity up to 0, what I said here. And we have a positive second derivative, which means that it's concave up from 0 to positive infinity, which I said here. An inflection point is where the sign of the second derivative changes. If I know what the sign of the second derivative is in my sine line, I can see that at 0 it changes from negative to positive. So we have an inflection point at that place. We could also have changed from positive to negative. It doesn't matter which way you go, as long as the sign of the second derivative is changing, you're going to have an inflection point in between. This is some of the justification for some of the features that we can find in functions. These are very common features to highlight and justify.